Satellite motion. Most of the time when we're talking about a satellite, we're talking about a relatively small object orbiting a larger object. Essentially, they're actually orbiting each other, but let's just focus on the small object for now. Gravity provides the centripetal force. So once again, that's centripetal, that's towards the center, to keep the satellite in this circular orbit, because the satellite wants to go tangential off out into space. So some examples of satellites, most of them, well, a lot of natural ones, like for example the moon. The moon is a satellite of the Earth, a natural one. All the planets are satellites of the sun. And then we have a bunch of man-made satellites. So there are a bunch of satellites. We have all kinds of satellites up there orbiting the Earth. And there's all kinds of international rules about where you can put them and so forth, so they don't crash into one another. But there's weather satellites, GPS satellites, military satellites, communication satellites of all kinds, thousands of them from many different countries. The main question here now is, how does an object become a satellite? Well, the answer is that the object must be given a proper tangential velocity. So it has to do with the actual speed, the actual size of the velocity, and the direction. The direction must be tangential. You can see it in this first diagram here on the left, a not-to-scale diagram. For example, if you were to throw a ball in the direction of V0, that green vector right there, a ball will curve to the ground. Because of gravity, it follows a curved path to the ground. If you throw it harder, it goes farther before it hits the ground. If you throw it harder yet, it goes farther. So this diagram here shows you somebody throwing a ball. If there's no air resistance, a ball does not slow down as quickly because of air resistance. Air resistance, in fact, doesn't slow the ball down, but because there's air resistance, balls do slow down in the horizontal direction and the vertical direction as well. They don't accelerate like 9.81. But let's ignore air resistance for a few minutes here. What happens here in the fourth case, actually the fifth case of this left-hand diagram, I'll highlight it in red. The ball is thrown sideways, but it starts to fall, and it follows a curved path. It's falling, 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 but also the Earth is a round object, and the Earth curves as the ball's path is curving, and what we say is that this satellite here, this ball, is falling around the Earth. It's a satellite of the Earth. Usually we have things up above the, well, all satellites are above the atmosphere because air at these speeds would burn them up, because this tangential speed here, this v sub 0, as indicated, is in the thousands of meters per second. In fact, near the surface of the Earth, or just outside the atmosphere, if you go about 100 miles up, the atmosphere is considered to go to about 70 miles up, and beyond that there's not much air anymore. But if you go up to 100, 200 miles, 300 miles, where like the space shuttle orbits or the space station, these tangential velocities are in the, around 18,000 miles per hour. So that's really, really fast. It takes a lot of energy to get them going. But once they're going, you don't need any fuel to keep them going. You launch them, and you get them up there, and you point them tangentially with that velocity, and they will fall, 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 fall around the Earth like this path. It's a satellite. It does not require any more rocket fuel once it's in that orbit, unless you need some minor adjustments, but no major fuel to keep it in that orbit. The second diagram here on the right shows you basically the same thing, except for if you have excessive speed, it turns out that satellites can go into what are called elliptical orbits, which is a special case, or a more general case of a curve. It's not an oval, but this one here, path D, I'll highlight that, is if you're above the necessary speed necessary for orbit, you have path D. And if you go really, really fast, if your tangential speed of launch is really great, you can escape a particular planet. For example, with the Earth, if your launch speed is right around 25,000 miles per hour, you can escape the Earth. You can go and escape the Earth's gravitational field. The old adage, what goes up must come down, is not true. If you throw a ball, even if you throw it straight up, this ball will never come back down. Or this object, if you launch it at that speed and you ignore air resistance, it will never come back. It will escape the Earth's gravity and possibly get sucked in by some other planet's gravity, or just go off into space indefinitely. So let's take a look at elliptical orbits. So orbits can be elliptical as well as circular. We like our man-made satellites to have the circular orbits, but Kepler, a scientist from the late 1500s, early 1600s, did a lot of work in optics and astronomy. He discovered that the planets, all the planets, if we still think of our 9 planets, including Pluto, they actually hadn't discovered all these planets yet, most of them, or at least some of them, that the planets have elliptical orbits. That was his first law. So let's take a look at an ellipse. What is an ellipse? Well, an ellipse is a set of all points in a plane at a given distance from 2 given points. Those 2 points are called foci. Foci is plural. Foci is plural for focus. So down in this first diagram here on the left, it shows you the blue path there would be a planet orbiting the sun, and the red segments there are the 2 segments that define the set of all the distances involved from the sun. I'll highlight it in red. From the sun to the planet, if you add up that distance plus that distance, that's the defined distance that actually defines the ellipse. For actual planets, the measure of how oval, quote unquote, how elongated the ellipse is called the eccentricity. A circle would be a case where the 2 foci would be 1 point, and you'd have an eccentricity of 0. Well, the maximum eccentricity is 1. The Earth has an almost circular path. Its eccentricity is 0.02, whereas there's a couple planets, especially Pluto, and so again I consider that a planet, its eccentricity is 0.25. It's quite elongated in its orbit. In fact, it's not always the farthest planet or object from the sun in our solar system. Sometimes Neptune is farther than Pluto. The second focus, the one focus is always the sun. The second focus point for our planets is just an imaginary spot in space. This second diagram here really hits at Kepler's second law, which I'm not really going to focus on too much here, pun not intended. But it it shows you an elliptical orbit of, say, a planet. All right, as the planet goes around the sun in this elliptical orbit, sometimes it's closer to the sun than other points, like points A and B are close to the sun. It turns out actually that the Earth in the our wintertime, the northern hemisphere wintertime, is closer to the Earth than it is during the summertime. In fact, right now the southern hemisphere is having their summer, and we're I shouldn't say quite, a little bit closer to the sun now than we are during our summer, because in our summer we're out here somewhere. I'll just highlight it in red. Right now the Earth is right about here, somewhere in there, say going from A to B, as it goes around the sun. Now, one of the implications here, as planets go around the sun, they'll go around, and it's kind of like throwing a ball up into the air. When they go this way, going towards their farther distance from the sun, they're actually losing speed because they're converting kinetic energy into GPE. They're still moving, there's still kinetic energy here, but out at this spot out here, I'll just exaggerate this, at this spot right here, it's a long way from the planet, or the sun, so there's a lot of GPE relative to the sun, and there's some kinetic energy out there. I'll make that small. As the planet rounds and comes back, and it's over here, which it's close to that right now for the Earth, when it gets to this spot over here between A and B, it has a smaller GPE, I'm making that small, GPE, small, plus a larger kinetic energy, because the 2 energies add up to the same amount because of the conservation of energy. It's the same amount of energy in both spots, total, added together. What this really implies is that planets are going faster when they're closer to the sun. They're going a little bit slower in speed when they're farther from the sun. And it's even more exaggerated when you have the highly elliptical orbits like Pluto. For the Earth, it's not that big of a difference because our eccentricity is very small. It's almost a circular orbit for the Earth. Now, a geostationary orbit is an orbit above the equator, and this diagram kind of illustrates that. It's what's called a high-altitude geostationary orbit. It's about 1/10 the distance to the moon. I'll kind of circle it out here. That's what I'm talking about. But this orbit, I'll highlight the orbit now in red. This satellite is orbiting the Earth, but it has to be directly above the equator, because that orbit there that I just highlighted is a 24-hour period, which means it takes 24 hours for that satellite to go around the Earth. Well, in the meantime, the Earth is spinning at that same rate. So what happens is this satellite right here, I'll highlight it in blue, this satellite right here in blue, this one is kind of above Africa. This will be geostationary above Africa, say this point right here in Africa. I'll have to use red, I guess, in Africa. So that particular geostationary satellite is right above Africa, and it could be a satellite TV transmitter for the people that live in Africa, because as the whole thing rotates, as the satellite goes around and the Earth rotates, that satellite stays relatively, well, it stays stationary with respect to that point. So people in that area could put satellite dishes on their roofs of their houses and point it towards the satellite, and the satellite could beam them cable TV, well, not cable TV, it'd be satellite TV, dish network. We do the same thing in the United States of America. People pay a lot of money for that because these are expensive satellites. But once they're up there, they keep going. You don't need any fuel to keep them going. You might have a little bit of fuel just to kind of make some adjustments, but they keep orbiting day in and day out in the same spot and beaming information back to the Earth. And we can put other weather satellites up there, but a lot of weather satellites and communication satellites are a lot closer in these low Earth orbits down over here. One of the things about all these orbits is, once again, you have to have the right tangential velocity, and it has to be tangential. All right? When you're closer to the Earth, your tangential velocity has to be greater. When you're further from the Earth, the tangential velocity is less. Your orbit also, once again, the center of your orbit, or at least one of the foci, or if it's a circular orbit, let's just focus on circular orbits for now. The center of the circle of your orbit has to be the center of the Earth. You can't just orbit over the North Pole. You can have what's called a circumpolar orbit, an orbit that passes over the poles. Right, that's not pictured here in this diagram. In the diagram, in the low Earth orbits, it has 3 low Earth orbits. They're all kind of at different angles, and they can be at different altitudes. You've got to have all kinds of permission to put those satellites up there from different governments so they don't crash into one another. But as long as the center of the orbit is in the center of the Earth, you can have any angled orbit, and they can be orbits that go over the poles. I forgot to mention a geosynchronous orbit. It's like it's a high altitude orbit. It also has a period of 24 hours. That would just be an orbit that's 24 hours that circles the Earth, but not above the equator. It would be synced up with a 24-hour day, but not stationary with respect to the equator. As I mentioned earlier, all right, well, let me back up a little bit. There's this thing called escape velocity or escape speed. You can escape a planet's gravity if you have enough speed. Now, when they launch rockets, they launch them, as you can see here in this diagram, upward, but then they have to point them tangentially eventually to get them into your orbit, whether it's circular or elliptical. But if you give the right amount of tangential velocity, in this case it's labeled as 40,000 kilometers per hour, that's the escape velocity from the Earth. It turns out to be about, I think I mentioned before, it's about 25,000 miles per hour. And each planet or moon has an escape velocity, a velocity with which you need to escape that planet with an initial launch velocity of that. Now, you can escape the Earth with a slower velocity if you have a rocket with a lot of fuel on it. The problem is it's expensive to have all that fuel. So once again, the escape velocity is just an initial launch velocity of that much, and ignoring air resistance. And it turns out that with escape velocities, you can actually launch straight up at that velocity or tangentially, and the object will escape the Earth. Lastly here now, weightlessness. So true weightlessness. True weightlessness has never been achieved by any person. It would be a spot way out in space, beyond our solar system. If you're in our solar system, you're either orbiting a planet, a moon, or you're orbiting the sun. Actually, you're orbiting the sun while you're orbiting the planets and the moons. But you're basically, any satellite that's orbiting, which we all are, and all these objects are, they're basically in this perpetual state of free fall. You're falling around the object you're orbiting. It would be the same feeling you would have like if you go to Great America and you get on the giant drop at Great America. That's a free fall, at least for a brief moment of time. You feel weightless because the chair is not pushing up on you. So another example would be, like I said, the example would be the giant drop, or some other kind of giant drop at Great America, or some other kind of amusement park ride where you are in free fall. There's no normal force, so you feel weightless, at least for a time. The astronauts just are in that perpetual state of falling, falling, falling around the Earth. That's not true weightlessness, but effectively it's as if you are weightless.